$1 million in 1942 for a single locomotive, not a fleet, not a program, one machine, one enormous, shrieking, turbine-driven nightmare of ambition that the engineers who built it privately called the most complex piece of rolling stock ever assembled in the United States. A locomotive so far ahead of its time that the technology needed to keep it running simply did not exist yet. A machine that promised to rewrite the rules of American railroading and instead rewrote the definition of expensive failure. This is the story of the Pennsylvania Railroad S2, the locomotive that almost convinced an entire nation that steam could outlive the diesel age, and the brutal physics lesson that ended that dream forever. To understand why the S2 existed at all, you have to understand the Pennsylvania Railroad, not just as a company, but as a state of mind. By the early 1940s, the PRR, as its employees and passengers called it, was not merely the largest railroad in America. It was, by almost any measure, the most powerful private corporation on earth. It operated more track than most European nations had in their entire systems. It moved more freight, carried more passengers, and employed more workers than the next two American railroads combined. Its executives did not think in terms of what was possible. They thought in terms of what had not yet been attempted. The Pennsylvania Railroad had a saying, passed down through generations of engineers and managers like a corporate commandment, the standard railroad of the world. That was not a nickname. That was a declaration. Every decision the PRR made was made with the assumption that whatever they built, whatever they designed, whatever they ran on their tracks, would become the model that every other railroad on the planet would eventually copy. They were not in the business of following trends. They were in the business of creating them. So, in 1942, when the PRR's chief engineer, a precise and almost frighteningly ambitious man named Paul Kiefer, sat down to design the next generation of motive power for the railroad's premier passenger routes, he did not look at what other railroads were doing. He looked at what nobody had dared to do yet. And what nobody had dared to do yet was put a steam turbine on a passenger locomotive. The idea was not entirely new. Engineers had been theorizing about turbine-driven locomotives since the early 1920s, when the first marine turbines demonstrated that rotating blades could extract far more energy from high-pressure steam than any reciprocating piston arrangement could ever hope to match. On a ship, turbines were already dominant. In power plants, turbines generated electricity with an efficiency that made piston engines look primitive. The question was never whether turbines were better than pistons in theory. The question was whether anyone could make one work on a locomotive in practice. Kiefer believed he could, and the Pennsylvania Railroad believed in Kiefer. Baldwin Locomotive Works, the Philadelphia-based manufacturer that had built some of the most celebrated steam power in American history, received the contract. The specifications Kiefer handed them were unlike anything Baldwin had ever been asked to produce. The locomotive would not drive its wheels through connecting rods and pistons in the traditional manner. Instead, a single large steam turbine mounted in the center of the machine would spin at enormous speed, and that rotational energy would be transmitted through a system of reduction gears directly to the driving axles. No reciprocating motion, no hammer blow on the rails, no connecting rods thrashing back and forth like mechanical windmills. Just a turbine, turning, 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 delivering power with a smoothness that no conventional steam locomotive could ever replicate. The numbers Kiefer promised were extraordinary. 6,900 horsepower. On paper, that figure was not just competitive with the best diesel locomotives of the era. It was dominant. It made the diesel look like an interim technology, a stopgap measure invented by men who had given up on steam too quickly. If the S2 worked as designed, the Pennsylvania Railroad would have proof that steam was not dying. Steam was evolving. Steam was becoming something faster, smoother, more powerful, and more efficient than anything the diesel engineers had imagined. Baldwin delivered the locomotive in 1944, and when it rolled out of the Eddystone plant for the first time, it looked like nothing America had ever seen on rails. The S2 was enormous. At over 37 meters in length, it was longer than many of the buildings that lined the streets of the cities it would serve. Its streamlined shroud, designed by the industrial styling firm that had given the PRR's passenger locomotives their distinctive Art Deco profiles, wrapped the entire machine in a skin of brushed steel that made it look less like a locomotive and more like a weapon. There were no visible connecting rods, no reciprocating motion visible from the platform. Standing beside it, passengers waiting for their train would have had no way of knowing they were looking at a steam locomotive at all. It looked like the future. It looked like something out of a science fiction serial, a machine designed by men who had decided that the 20th century was not moving fast enough. The first test runs were promising in the way that first test runs always are, when everyone involved desperately wants them to be promising. The turbine spun cleanly. The reduction gears transmitted power efficiently. The locomotive moved. It accelerated. It reached speeds that made the dynamometer car trailing behind it print numbers that PRR executives framed and hung on their office walls. But the engineers in the cab knew something the executives did not, or rather, they knew something the executives chose not to hear. The S2 was only magnificent when it was going fast. At track speed, above 65 miles per hour on a level grade, with a clear block signal ahead, the turbine found its operating point, and the locomotive justified every dollar of its extraordinary cost. The reduction in vibration alone was revelatory. Conventional steam locomotives at high speed shook with a violence that experienced crews simply accepted as the nature of the machine. A constant hammering that loosened bolts, fatigued metal, and required maintenance attention after virtually every long run. The S2 at speed was almost eerily smooth. The turbine's rotational motion transmitted its power without the characteristic surge and thud of pistons. The ride was, by steam standards, almost civilized. But railroading is not conducted at constant high speed on level grade. Railroading is conducted in the real world, where trains leave stations from a complete stop, where grades slow progress to a crawl, where signal delays force reductions in speed at inconvenient moments, where the same locomotive that just completed a glorious high-speed run between Philadelphia and New York must now back into a yard, pause for servicing, and then build back up through all the speeds it hates before it reaches the speeds it loves. And the S2 hated low speeds with a passion that bordered on self-destruction. Steam turbines are designed to operate within a relatively narrow band of rotational speed. Too slow, and the blade geometry that makes them efficient becomes a liability. Too slow, and the steam passes through without imparting its energy properly. The turbine still demands steam, still demands fuel and water, still demands the fireman's constant attention, but it delivers back only a fraction of what it takes. The thermodynamic efficiency that made the turbine so compelling in theory became, at low speeds, a brutal reversal. The S2 below 40 miles per hour consumed steam at a rate that made the firemen who worked it stare at their gauges with an expression that experienced PRR observers described as quiet desperation. Crews developed a phrase for the S2's behavior on the main line. They called it the speed or starve problem. Give it speed, and it was a revelation. Make it slow down, and it became the most expensive coal-burning boiler anchor in the history of American transportation. The numbers were stark. At operating speed, the S2's thermal efficiency compared favorably to the best diesel-electric units, then entering service on competing railroads. At 30 miles per hour, it burned 3 times the fuel per ton-mile of a conventional steam locomotive. 3 times. For a railroad that moved millions of passengers annually, that figure was not an engineering footnote. It was a financial catastrophe in slow motion, and the S2 could not avoid being slow. The PRR's main line between New York and Chicago passed through multiple terminal cities where speed limits, platform approaches, and switching movements made low-speed operation unavoidable. Every time the S2 crept into Harrisburg or trundled through the Pittsburgh terminal, it was burning money at a rate that no dynamometer record could justify. The maintenance crews discovered the second problem within the first months of service. The reduction gears that transmitted the turbine's rotational speed down to the rotational speed of the driving wheels were, by the engineering standards of 1944, works of extraordinary precision. They had to be. The turbine ran at speeds that no conventional locomotive component had ever been asked to sustain. The gears stepped that speed down through multiple reduction stages, and each stage imposed loads on the gear teeth that engineers had calculated carefully, and that the gears, in theory, were more than adequate to handle in theory. In practice, the gears operated in an environment that the calculations had underestimated. The heat generated by a steam locomotive in full operation is not merely the heat of combustion in the firebox. It is the accumulated thermal output of every system operating simultaneously. The firebox, the boiler barrel, the steam pipes, the turbine casing itself. The S2 concentrated this heat in a smaller enclosed space than any conventional locomotive because its shrouded body trapped it. The oil lubricating the reduction gears ran hotter than the engineers had anticipated. Hotter oil is thinner oil. Thinner oil is less effective oil. And less effective lubrication on precision reduction gears that were already operating at the outer edge of their rated capacity meant one thing. The gears began to wear faster than anyone had budgeted for. Not catastrophically, not dramatically. The S2 did not throw a gear tooth in a shower of metal shards on its first revenue run. It degraded, slowly, consistently, with the patient, inevitable persistence of metal against metal under loads that were just slightly, just fractionally, just barely beyond sustainable. The maintenance intervals that Baldwin had estimated began to compress. A gear inspection that was supposed to be a 30-day routine became a 20-day necessity, then a 15-day urgency, then a problem that was occupying more of the PRR's mechanical department's attention than any single locomotive had any right to demand. The servicing requirements also confronted the crews with the S2's most intimate indignity. Conventional steam locomotives, for all their complexity, were mechanisms that experienced crews understood in their bones. A leaking piston gland announced itself through familiar sounds. An overheating axle box gave off a smell that veterans recognized before any instrument confirmed it. The diagnosis of a conventional steam locomotive's ailments was, to a significant degree, a skilled craft practiced through sensory experience accumulated over careers. The S2 was not that kind of machine. Its turbine and gear train were not mechanisms that anyone in the PRR's maintenance force had trained on, because nobody in American railroading had ever operated a machine like this before. When something was wrong with a turbine, the first indication was often not a sound or a smell, but a reading on a gauge that most crews had to check against a reference card to interpret correctly. The specialized knowledge required to keep the S2 running was knowledge that the railroad was essentially inventing in real time, on the job, with an operational locomotive and paying passengers in the cars behind it. Kiefer's team worked continuously on refinements. Lubrication specifications were revised. Heat shielding was added around the gear cases. Operating procedures were updated to minimize time spent at the low speeds that punished the turbine's efficiency. The PRR, which was not an organization that abandoned expensive commitments easily, was determined to make the S2 work. There were days when it seemed possible. On the Philadelphia to Chicago runs, when the dispatcher gave the S2 a clean board and the track was straight and the schedule allowed full throttle for extended stretches, the locomotive performed with a quality that silenced skeptics, not with noise, but with its absence. Passengers in the first-class cars reported a smoothness of travel that they had not experienced on any previous Pennsylvania Railroad service. The absence of the surging rhythmic push of conventional steam connecting rods transmitted through the train at each piston stroke created a ride that felt qualitatively different. Felt, literally, more modern. But the Revenue Department's figures told a different story from the passenger comfort surveys. The cost per mile of operating the S2 was running at multiples of what the PRR's conventional steam locomotives delivered. The locomotive was not earning its keep. It was demonstrating its capability at enormous ongoing expense. And there is a point in every engineering program where demonstrating capability and running a railroad begin to pull in incompatible directions. That point arrived for the S2 in 1946. The war was over. The nation's railroads were transitioning from wartime operation to peacetime competition. And peacetime competition meant something new and genuinely threatening. The General Motors Electromotive Division had spent the war years quietly perfecting its diesel-electric locomotives, and it was now deploying them on American main lines in numbers that the railroad industry had not anticipated. The EMD F unit was not glamorous. It was not enormous. It did not make the ground shake when it passed. It was, in almost every aesthetic dimension, profoundly unimpressive compared to the S2. But it started with a key turn. It operated efficiently at any speed. It required less maintenance per mile than any steam locomotive ever built. And it could be operated by a single crew member with less specialized training than the S2 demanded from two. The financial arithmetic was not complicated, it was devastating. The PRR, which had committed more deeply to steam traction than almost any other American railroad, found itself looking at the S2 not as the future, but as the most expensive proof of concept in its history. The turbine locomotive had demonstrated something, certainly. It had demonstrated that steam turbine drive was mechanically feasible. It had demonstrated that high-speed efficiency was achievable. It had demonstrated that passengers appreciated the quality of the ride it provided. What it had also demonstrated with equal clarity was that none of those achievements were sufficient to justify the costs. The decision to retire the S2 was not announced with drama. The PRR was not an organization that enjoyed public admissions of difficulty. Internal memoranda from 1949 describe the process in the flat, procedural language of institutional accounting. The locomotive's maintenance cost per revenue mile had reached a figure that could not be reconciled with continued primary line operation. The turbine reduction gear system required a level of component replacement frequency that was, the documents noted with admirable understatement, inconsistent with efficient fleet management. The S2 was withdrawn from service. Baldwin was not asked to build a second one. The PRR's engineering department filed the project documentation carefully because the Pennsylvania Railroad filed everything carefully and moved on to the task of evaluating diesel alternatives with the focused attention of an organization that had learned an expensive lesson and intended not to repeat it. There was no ceremony, no fanfare, no crowds lining the platform at Philadelphia's Broad Street station to watch the turbine locomotive make its final run. The machine that had cost $1,001,942 simply stopped appearing on the roster, replaced by a growing fleet of diesel electrics that were cheaper to buy, simpler to maintain, and entirely adequate for everything the S2 had done, except for those moments of transcendent high-speed smoothness that only the people who had ridden behind it at full throttle would ever understand. The S2 was scrapped in 1949, 5 years of service, $1 million. And a question that the American railroad industry has never quite stopped asking: what would have happened if the technology had been just slightly more mature? If the reduction gears had been engineered with the precision that would not become available until the following decade? If the specialized lubricants that high-speed gear systems require had been developed before the locomotive was built rather than after it was retired? The frustrating answer, the one that engineers who study the S2 still articulate with a particular kind of regret, is that the concept was not wrong. Steam turbine locomotives did work in other contexts. Swedish and British engineers developed turbine-drive steam locomotives in the same period that performed with considerably greater operational reliability, though never at the power levels the S2 attempted. The principle was sound. The engineering was genuine. The investment was real. The problem was timing. The S2 arrived at the intersection of two technological trajectories: steam technology that was approaching the end of its development curve, and diesel technology that was at the beginning of it. The turbine locomotive represented the absolute frontier of what steam could become, and that frontier was not far enough ahead of where diesel already was to justify the cost of reaching it. In the archives of the Pennsylvania Railroad Historical Society, the documentation of the S2 program fills multiple boxes: stress calculations, thermodynamic analyzers, gear geometry specifications worked out to thousandths of an inch, maintenance logs recording every component replacement, every oil analysis, every torque reading taken during the 5 years the locomotive was in service. It is an extraordinary record of human effort directed toward a machine that the market had already decided it did not need, even before the machine was finished. The Standard Railroad of the world had built something genuinely unprecedented, something that pushed against the limits of what steam could do with a force that no other railroad on earth attempted to match. And it had discovered, at the cost of $1 million and 5 years of maintenance headaches, that pushing against limits is not the same as moving past them. Today, there is nothing left of the S2, no preserved example in a museum, no monument at Broad Street Station. The locomotive that was supposed to demonstrate that the Pennsylvania Railroad's faith in steam had not been misplaced was consumed by the same economy of industrial progress that consumed the steam age itself. But the records survive, and in the records, in the maintenance logs and the dynamometer readings and the internal memoranda written in the careful bureaucratic language of an organization trying to understand what it had built, there is something that feels like an answer to a question that the railroad industry spent 20 years asking. They built the perfect steam locomotive too late, and they knew it, and they built it anyway, because the Pennsylvania Railroad was the standard railroad of the world, and the standard railroad of the world did not admit that a problem was unsolvable until it had spent $1 million proving it. That is not a story about failure. It is a story about the kind of ambition that produces the most honest engineering lessons, the kind you can only learn by going all the way to the edge and looking over. The S2 looked over. It did not like what it saw, and it told everyone exactly what was down there. Nobody listened, but the diesel was already on its way.